Imagine this. It's the early days of plastic getting integrated into cars. Engineers have this new miracle material called nylon. It's strong, it's lightweight, it's cheap, it's easy to mold, and at this point, it's showing up everywhere. Gears, bushings, hoses, brackets, all sorts of parts. So somebody says, awesome, hey, this is great material. Let's make fuel lines out of it. Well, sure, why not? Seems logical, right? Plastic doesn't rust like steel, it's lighter weight, it's more flexible, it should be perfect. Except it wasn't. Those early nylon fuel lines slowly absorbed moisture from the air. Not liquid water, just humidity in the air. Water vapor in the air itself. As they absorbed that moisture, the plastic would swell. It would grow slightly in size, it would soften, and stiffness would drop. And once that started happening, tolerances would drift, clamps would loosen, seals would stop fitting the way they were designed to fit. Suddenly you're dealing with leaks and cracking, and in some cases, complete failure under pressure. That's not just an annoying little problem. This is actually dangerous. These are fuel systems, pressurized lines, hot engines. You absolutely cannot have a critical system in a vehicle that slowly changes shape every time the weather changes. So engineers were stuck with a brutal problem. The plastic was strong, it was cheap, it was easy to manufacture, but it could not stay dimensionally stable in the real world. And this one problem didn't just trigger a small tweak. It forced the chemists to rethink how nylon itself was built. This is a big reason why we actually now have an entire family of different nylons, all engineered for different environments and different behaviors. Now, before we go deeper, a little bit of quick context. Here at Vision Miner, we specialize in high temperature and advanced materials 3D printing, and we've been doing it for nearly a decade. Everything from PEEK and Ultim to nylon and polycarbonate. These are the kinds of materials that we work with every single day in real environments with real customers. We're doing a broader series on the materials that we print, some of which you've probably printed yourself. So today, this is the story behind why PA12 or nylon 12 or polyamide 12 is way more interesting than most people realize. So by the time engineers were running into these moisture problems, nylon was by no means new. Nylon 6 and 6,6 had been around since the 1930s. They were wildly successful in textiles and clothing, industrial parts, consumer goods. But they all had one big flaw, that they loved water. Later on, nylon 11 came along and solved a lot of the issues with moisture, but it was made from castor beans, and that means agricultural supply swings, pricing volatility, and limits on scaling for heavy industry. When the crop determines your output, there's more limits for industrial scale production there. So the world wanted a nylon that behaved more like nylon 11 in moisture stability, but could be produced more reliably from petrochemical feedstocks and stayed dimensionally stable in harsh environments. And that is the gap that PA12 was created to fill. So let's get into a little chemistry. Nylon is made from long molecular chains. Imagine microscopic spaghetti strings. Along all those chains are chemical groups called amide groups. Amide groups act like tiny little magnets for water. They naturally attract and bond with water molecules that are just floating around in the air. In nylons like nylon 6, which is still widely used today, those water attracting groups are packed fairly close together along that chain. So the material slowly absorbs moisture from the environment, almost like a sponge at the molecular level. And once the water gets inside the plastic, it actually pushes those molecular chains slightly apart. It's microscopic, but it happens everywhere inside the part consistently. When you scale that up across millions and millions of molecules, the entire part ends up changing shape just a little bit. Dimensions move, the stiffness goes down, and mechanical behavior shifts a little bit. For clothing and textiles and consumer products, this can be totally fine, not a big deal, but when it comes to fuel systems or brake tubing or precision mechanical components, or basically anything that's safety critical, then that behavior is unacceptable. Engineers didn't need a stronger nylon, they needed a drier nylon, one that simply didn't care about water and moisture. Now, this is where the engineers got clever. Instead of trying to coat the plastic or block the moisture with something from the outside, they asked a simple question. What if we just spaced the water-attracting groups further apart inside the molecule itself? So here's the mental image. Imagine a string with little magnets tied along it. If the magnets are packed tightly together, they grab everything around them. But if you spread those magnets further apart, their overall pull becomes much weaker, and so it maintains its shape. See that? Interesting prop example. Took me a long time to tie these all together and make this. Now in chemistry terms, that means they needed to build the nylon chain with longer carbon segments between each amide group. More spacing between those water-attracting groups means fewer water magnets per inch of chain, and that one structural change dramatically reduced how much moisture the plastic could absorb, several times less than older nylons. And once that happened, everything changed. The plastic now stayed stiff, the dimensions now were more stable, and the mechanical properties stayed predictable, even in humid or wet environments. And that material became what we now know as nylon 12, or PA12, or polyamide 12. And by the way, PA just stands for polyamide. You'll see that everywhere. PA6, PA11, PA12, and many others. This wasn't just a random lab accident. In the mid-1960s, a German chemical company called Chemische Werk Hulls, now part of Evonik, commercialized PA12 under the brand name Vestamid. Some of you might recognize that name from certain nylon filaments that hit the market over the last few years. Now, there was a very practical driver behind this development, and it was really supply chain stability. Nylon 11 was awesome. It had great moisture resistance, but it relied on the castor bean agriculture, which means crop yields from year to year, from month to month, would fluctuate. You get less beans and more beans. The weather affects the supply. If you get a hurricane or something one year, then all of a sudden, okay, no more supply for nylon 11. The prices would move up and down depending on demand. You know, if another product came out using castor bean oil, okay, now there's demand for that. So all of this created risk for the large-scale industrial manufacturing. To be able to consistently produce large amounts of this polymer to keep the prices low enough for everybody to use it in their products, you gotta have consistency. PA12 now could be produced reliably from petroleum feedstocks, oil, at a massive scale. So it checked both boxes, the low moisture absorption and the industrial scale predictable supply chain. It wasn't just better chemistry, it was overall better manufacturing economics. So the first major proving ground for PA12 was automotive. You know, we had the fuel lines, air brake tubing on trucks, fluid handling systems exposed to vibration and temperature swings and road salts and fuel and pressure and all kinds of stuff. It didn't swell, it didn't crack easily, it stayed flexible even in freezing temperatures, which is huge, and most importantly, it didn't care about the humidity. That reliability is why it quietly became an industry standard, even though most consumers probably have never heard of it. Over time, other industries started paying attention. In medical applications, PA12 showed up in the tiny catheter tubes that need high burst strength while still bending smoothly through blood vessels without kinking. In sports equipment, it found a home in high-end ski boots and performance footwear that needs to stay tough and impact resistant at freezing temperatures. In oil and gas industry, it's been used in flexible piping liners that can live for decades, even in the aggressive chemical and saltwater environments like out on an oil rig. Many different industries, the same core advantage: stability under real-world conditions. So here's the twist. PA12 was never designed for 3D printing or with 3D printing in mind, but its chemistry kind of accidentally made it almost ideal for it, assuming you have the right machine and thermal control to be able to print it. It's got a really clean, just overall melting and solidification behavior. It doesn't warp super wildly or aggressively when it's heated and then cooled. It holds really good dimensional accuracy very well, and it doesn't aggressively absorb moisture like many of the other nylons. Many of you probably know if you leave your nylon spool out overnight, it's done. You gotta dry that thing again. PA12, not so much. You should still dry it, but it can last a lot longer in open air. And we see this in the SLS as well. With the SLS powder, it pretty much sits out in the open air until it gets printed, and we've experienced no issues with that on the Formlabs SLS machines. We have seen issues with that on other machines, so it does probably depend on where you're getting your raw SLS powder. Now, if you've ever ordered an industrial SLS printed part from a major service bureau, then there's a very high chance it was just Nylon 12. Even HP's multi-jet fusion platform is entirely built around Nylon 12. And most other SLS systems also rely heavily on PA12 as the core production material. We run a ton of PA12 ourselves, both in the powder systems like the Formlabs Fuse 1, which you can find at visionminer.com/formlabs, and of course machines in FDM like our 22 IDEX, plus large format industrial systems like the Hilo if you need larger oversized parts. What we really see firsthand here at Vision Miner is that PA12 behaves pretty predictably compared to its more moisture sensitive siblings like Nylon 6. Once you dial it in and you tune it, then it runs consistently. It holds tolerances really well. It scales cleanly in low and medium volume production without constant babysitting. I mean, that consistency is a really big deal in real world manufacturing. In fact, I just came into the office this morning and the guys had just pulled out a massive part. Bigger than this, it was almost the full build volume of our 22, and it was a duct, and it was for an aerospace customer. We called them and asked, and we couldn't show it off in the video today, but it was a massive part, really big. Just a big old duct, printed clean and reliably. You don't want to come in the next day and see that, oh, it failed extrusion or something 3 hours into a 27-hour print. You know, it's not the situation you like. So having good materials that print cleanly and consistently is key, especially on a machine that's reliable like the 22 IDEX. And Nylon 12 is almost 60 years old, and somehow it's almost more relevant than ever. Modern manufacturing cares about different things from the consumer industry. They care about repeatability, dimensional stability, environmental robustness, lightweight performance, and predictable processing. Nylon 12 checks all of those boxes. Here at Vision Miner, our core bread and butter has always been the high temperature materials like Peak and Ultim. That's where we live, that's where we work, that's what we do every day, but advanced nylons have been a huge part of our life, especially PA12. They're a huge part of what we run for customers, you know, for tooling and fixtures and housing, functional parts, and a lot of our customers just run that. They run nylons and polycarbonates all day in, day out, for months at a time. That's just what they do. Now, one of the biggest reasons for the success with it is the same reason PA12 exists in the first place, controlling how the material behaves in the real world and moisture absorption. It doesn't absorb a lot of moisture, which makes it a lot better for 3D printing. Now, our 22 IDEX is exceptionally well suited for Nylon 12 and Nylon 6 because of the heated chamber, and so your spool actually sits in the heated chamber so it stays dry. But having that stable thermal environment is crucial. When you have that, you get better layer bonding, less warping, better dimensional accuracy, more repeatability, all compared to open frame or hobby class machines. Now, these are the things that actually matter when parts move from test fit and prototype to real world production. End-use parts you're sending to customers, parts you're making thousands of. Now, if you want more technical data or material behavior, processing notes, data sheets, we've got all of that. Head over to visionminer.com or shoot us an email, give us a call. We've got a ton of knowledges and resources that we can share with you. And if you're trying to build a complete additive manufacturing workflow for your business, from the materials to the machines to the process, that's exactly what we help people with every single day. So the biggest takeaway from this video is that Nylon 12 wasn't created to be flashy. It was created to solve a fundamental, kind of boring, but very critical problem: moisture stability. And solving that problem properly is exactly why it's still one of the most trusted engineering plastics in the world. Anyway, I hope you enjoyed this video. Leave a comment if you want to see more like it, or give us a call, shoot us an email if you want to get some 3D printers, 3D scanners, advanced materials, and much more. So thank you so much for watching. Have a positive rest of your day. I'll see you on the next video.